Hello, everyone, and welcome back to the Water Online Show, powered by Water Online, the leading online destination for the water and wastewater market. And today's episode is all about something you've probably seen on spec sheets, calibration reports, and instrumentation data, but may not fully unpack every single day, and that is limit of detection, or LOD. What does it actually mean when an instrument says it can detect down to a certain level? How is that different from limit of quantification, and why does that distinction matter so much and also matter more than what most people actually think? We're going to dig into how LOD is determined, what those numbers really represent in real-world application, and how they should influence the way you select and configure instrumentation, especially when it comes to turbidimeters and low-level measurements. We also get practical, as we like to do here on the Water Online Show, on how LOD plays into signal outputs like 4 to 20 milliamp output, and what you need to consider to ensure your data is not just precise, but actually meaningful and impactful. And finally, we'll point you to where you can go deeper, including how companies like Lovibond are approaching measurement and instrumentation in this space specifically. If you've ever questioned whether your readings are truly telling you something or just giving you a number, this episode's for you. So let's get into it. I'd like to bring in our guest, if I may, Mr. Mike Sadar with Lovibond. Mike, welcome to the Water Online Show.
Thank you, Travis.
So I want to go right off the bat here and get some definitions from you, if I could. That definition that I'd like to dig a little deeper on here is, give me the definition of LOD, but also give me the definition of LOQ and how they're different.
Sure. So the LOD is known as the limit of detection, and it's defined as the minimum detectable change in the concentration of an analyte by an instrument. So in process turbidity, for example, that is the minimum change in turbidity that an instrument can detect that is truly due to turbidity and not due to instrument noise or ambient noise. The LOD is a specification that is from a family of detection and quantification specifications, and it's the most common one these days.
Yeah.
And what it really means is you're able to detect this analyte, but you not necessarily can quantify it. And LOQ is the ability to quantify a given analyte. And it's once you determine what the LOD is, you multiply that value by a factor of 3, and you get to the LOQ.
So what was that word you used? Amylite? Am I saying that right?
It's analyte.
Analyte. Okay. So for somebody like me, who I have a pretty solid understanding of water and wastewater, but I still have no idea what that term refers to. What is that?
So an analyte is essentially a compound or characteristic in a water or wastewater sample that you want to test for.
Got it.
In most cases, analytes are things such as chlorine, where you need to test it, know what its level is, or turbidity to know if your filtration is proper and that so forth. So anything that you want to test in a given sample of water is technically an analyte.
That makes sense. Thank you for clarifying on that. So what tests are used to determine LOD, but also more specifically, if we could take it a step further, what does that number really mean?
So the test that we use to determine the LOD is basically at the very bottom of the measurement range of an instrument. And you want to be able to determine at what level above the instrument and ambient noise do you have to be able to detect to actually know it's indeed an analyte and not some artifact of the instrument itself. And most common thing that instruments have is called electronic noise from the electronics. So an analyte detection, that has to stand up and above that electronic noise. And we do a test where we spike a very, very clean water sample with the analyte. In this case, we talk about turbidity, where we'd spike a small amount of turbidity above a filtered water that is flowing through a process turbidimeter, and we would measure the noise of that spike. And we do this repeated times, and we take the average of that noise, and we express that noise as a standard deviation. Okay. And that is the basis for LOD. And what we do is we multiply that standard deviation of that noise, of that spike, by a factor of 3 to get your LOD. And then to get to the LOQ, the limit of quantification, we would multiply that by 10.
Okay. Got it. All right. So what can that actually tell us though? So from an outcome standpoint, what are we looking for? What is the desired outcome of learning that information?
So basically, in order to detect a sample by a given instrument type or a given brand of instrument or a method, your LOD needs to be above the number that's stated to be able to detect that analyte in using that instrument. So for example, if you have an LOD that is 0.05 NTU and your instrument only reads down to 1 NTU, it's the wrong instrument. You can't see you cannot see what you need to of the analyte. So you would have to get an instrument that is more sensitive, that would have a lower LOD to be able to detect those trace amounts of analytes.
That makes sense, but I'm curious, how does it apply when selecting a turbidimeter for measurement? Like, what are we talking about in terms of application here? If you're going through the selection process, like, what are we looking at there?
So it definitely depends on your application. So in most cases, your LOD is important if you're looking for trace amounts of an analyte, and you need to get an instrument that's the bottom end of a measurement range. So typically, if you have a regulated compound or a regulated analyte, turbidity is one, then you have to have an instrument that can detect at least down to the regulated value, and preferably you can detect way below that regulated value so that you actually have room for adjustment of your processes to be able to maintain and achieve whatever the regulatory limit of an analyte might be.
So then, if we're looking at that on that level, how is it used to set outputs? Like, because in the introduction, I talked about 4 to 20.
Yes.
So I'm curious how it's used to set those outputs.
Sure. So the LOD is really, really important on setting the outputs because usually on turbidimeters, process turbidimeters in particular, you do have a value that is displayed at the actual screen that's on the instrument.
Mm-hmm.
And that is usually a digital signal. But when you transfer that signal to a data collection system or a data management system, such as a SCADA system, typically you use an output, and that output, the most common one that is used is a 4 to 20 milliamp output. It's analog output. It's been around for 50 years, but almost everybody understands it. And so what you have to do is you have to make sure that your processor that defines that analog output is sufficient enough to be able to match or be a little bit better than the LOD.
Mm-hmm.
So a simple example is most turbidimeters have what's called a 12-bit processor, and
12-bit processor. Okay.
And so their analog output you'll be able to define how many steps, or how you basically divide that 12-bit processor into individual but equal steps.
Yeah.
And for a 12-bit processor, that's 4,096 steps. So if you...
It's a lot of steps.
It is a lot of steps. And what happens, and what people often do, is they'll say, okay, I'll take my analog outputs, I'll put the 4 milliamp at 0 turbidity units, and I'll put the 20 milliamp at the maximum range of the instrument.
Sure.
What happens is, if say you have 100 NTU range, which is like on our Lovibond process turbidimeter, that's our top end, then you divide that by 4,096. What you get is a value of 0.02.
Okay.
And so basically that analog output can determine the highest resolution it can determine, or change in turbidity, is 0.02 turbidity units. So if an instrument has an LOD that is less than 0.02, that's fine. You can
that's good.
You're good.
Okay.
If the LOD is above it, then what you have to do is you have to adjust.
You're in trouble.
You're in trouble because you're not going to match it.
Okay.
The other thing that you can do is what most water plants do is they want to get as much resolution down at the bottom that they can get with their 4 to 20.
Sure.
What they'll do is they'll squeeze the concentration down that they're outputting. So instead of squeeze the range down that they're outputting. So instead of going 0 to 100, they might go 0 to 20, where they can see a higher resolution down even below the LOD value. So for example, if you take the LOD and you know your processor, say our LOD is 0.002 turbidity units, which is
let's say that.
Process
that's common, right?
Yep. And if you want to know, well, what's the range where I can really optimize my output? Well, take your processor and you know there's 4,096 steps, multiply that by the LOD. I'll give you the steps that you can take to see changes that are equivalent to the LOD. And that gives you the highest resolution that the instrument can define that you can actually push into your SCADA system with. And so what it does is it gives you very good, accurate readings at the bottom end of the measurement range.
Got it. So there's a lot of math there. I followed it, most of it. I'm sure all of you out there are a lot smarter than I am, so you're able to sort of follow that math. So that's all good, right? So I think we're good there. What I am curious about, though, is take a water plant, for instance. What are some of the issues or problems or things they should look out for that would lead them to you? That would lead them to, say, a turbidimeter for measurement, start looking at LOD. What symptoms exist out there in a water plant that an operator or an engineer would look at and be like, oh, we need a little help here, or I think there's something off?
So as filtration from drinking water has evolved over the last couple decades, there's been a push both from the regulatory side, but also from the drinking water plant side to put out the best water they can put out for the customer, the consumer.
Of course, that's every water plant's goal, right? Put out the best, cleanest, safest water.
Yeah. So what they need is so what they're doing is they're pushing the processes to make this clean water better and better and better. And so that means if you're going to push the filtration to higher levels or make the performance better, then you have to have instruments that have better LODs to be able to detect problems when they occur.
Right.
And so one of the things that water plants are all afraid of is having a filter breakthrough.
Yep.
And so if you keep pushing the water plant's performance to lower and lower levels, and you start seeing a trickling of particles coming down through a conventional filter,
that's bad.
You might get a little bit of noise.
Yeah.
And that is going to be able to be detected by a really good instrument with a really low LOD versus an instrument that maybe is 30 or 40 years old that has a much higher LOD.
And that's where you come in, right? So I'm curious for all of our listeners out there and for our viewers, where can someone learn more about LOD and Lovibond's instrumentation? I'm going to bring them right back to your doorstep as to how you can help. Where could they find you and how can you help?
So we have a lot of white papers on LOD and low-level turbidity measurement on lovibond.us. And there's also a lot of content on Water Online.
I've heard of that place. Yeah.
Has this kind of information as well.
Fantastic. So, I mean, one thing I do want to end with is a lot of times here on the Water Online show, I'll ask the question, what is the most logical first next step for a water plant out there? What should they do first to either identify if they have an issue, or if they've identified they have an issue, what should they do first? And maybe it's as simple as they go to lovibond.us. I don't know, but is there any first step recommendations that you could give a water plant engineer or operator who may be dealing with this or may be dealing with it and not even know it? What would be like the first most logical next step?
So if you have a concern, the first thing is check your measurement system.
Right.
Make sure it is measuring properly.
Yep.
And the most simple way to do it, and what a lot of water plants do, is they grab a sample of a process turbidimeter or a process instrument and measure it in a laboratory setting.
Yeah.
Because the laboratory instrumentation typically has very low LODs or very good LODs, and they're going to be able to confirm whether or not it's actually happened, or maybe there's an issue with the instrument. Once you get past that, then the next thing you would do is start looking for what's causing the issue that you're concerned about.
Right. So then you go to the cause. Like
Yes.
you identify that something's off, right? Something's not working, or your numbers aren't as accurate as they need to be, or something just is off about the technology you currently have. And then you can kind of go into, all right, so what are the possibilities and what are the ways that we can go about fixing this potential issue? So all of that makes sense. I know it makes sense to our viewers, to our listeners out there. Big thank you to Mike Sadar with Lovibond for challenging some of the assumptions we hold about limit of detection and reminding us that real progress in this industry isn't about one singular way of thinking. It's about how we think, decide, and lead as a team. Because at the end of the day, the future of water won't be defined by the tools we adopt specifically, but it will be defined by the choices that we make with them. And that's exactly where Water Online comes in. Our goal isn't to just showcase new solutions, it's to help bridge the gap between what's possible and what actually works in the field, like the Lovibond turbidimeter. So whether it's through conversations like this, case studies, technical insights, or connecting utilities with solution providers who truly understand their challenges, everything we do is about helping make smarter, more confident decisions. So if you're a utility trying to navigate digital transformation or measurement or any of those things that we face on a daily basis as an industry, or perhaps you're a technology provider trying to better serve the marketplace, this is the work that's in front of us. As always, thanks for listening to the Water Online Show. If you found this episode valuable, be sure to subscribe, smash that like button, share with a colleague, and stay connected with us at wateronline.com. Until next time, keep pushing the industry forward.